Good day, everyone! Today, we are going to discuss the lithosphere, which is the solid outer part of Earth. The lithosphere includes the brittle upper portion of the mantle and the crust, the outermost layers of Earth's structure. It is bounded by the atmosphere above and the asthenosphere, another part of the upper mantle, below. There are two types of lithosphere: oceanic lithosphere and continental lithosphere. Oceanic lithosphere is associated with oceanic crust and is slightly denser than continental lithosphere. Earth consists of three main layers: the crust, the mantle, and the core. The core accounts for almost half of Earth's radius, but it amounts to only 16.1% of Earth's volume. Most of Earth's volume, 82.5%, is its mantle, and only a small fraction, 1.4%, is its crust. The Earth's outermost layer, its crust, is rocky and rigid. There are two kinds of crust: continental crust and ocean crust. Continental crust is thicker and predominantly felsic in composition, meaning that it contains minerals that are richer in silica. The composition is important because it makes continental crust less dense than ocean crust. Ocean crust is thinner and predominantly mafic in composition. Mafic rocks contain minerals with less silica, but more iron and magnesium. Mafic rocks, and therefore ocean crust, are denser than the felsic rocks of continental crust. The crust floats on the mantle. Continental crust floats higher in the mantle than ocean crust because of the lower density of continental crust. An important consequence of the difference in density is that if tectonic plates happen to bring ocean crust and continental crust into collision, the plate with ocean crust will be forced down into the mantle beneath the plate with continental crust. The second layer is the mantle, which is almost entirely solid rock, but it is in constant motion, flowing very slowly. The mantle lies between Earth's dense, superheated core and its thin outer layer, the crust. The mantle is about 2,900 kilometers, 1,882 miles thick, and makes up a whopping 84% of Earth's total volume. The mantle is divided into several layers: the upper mantle, the transition zone, the lower mantle, and D double prime, the strange region where the mantle meets the outer core. The upper mantle extends from the crust to a depth of about 410 kilometers, 255 miles. The upper mantle is mostly solid, but its more malleable regions contribute to tectonic activity. Two parts of the upper mantle are often recognized as distinct regions in Earth's interior: the lithosphere and the asthenosphere. The lithosphere is the solid outer part of Earth, extending to a depth of about 100 kilometers, 62 miles. The lithosphere includes both the crust and the brittle upper portion of the mantle. The lithosphere is both the coolest and the most rigid of Earth's layers. The most well-known feature associated with Earth's lithosphere is tectonic activity. Tectonic activity describes the interaction of the huge slabs of lithosphere called tectonic plates. The lithosphere is divided into 15 major tectonic plates: the North American, Caribbean, South American, Scotia, Antarctic, Eurasian, Arabian, African, Indian, Philippine, Australian, Pacific, Juan de Fuca, Cocos, and Nazca. The asthenosphere is the denser, weaker layer beneath the lithospheric mantle. It lies between about 100 kilometers, 62 miles, and 410 kilometers, 255 miles, beneath Earth's surface. The temperature and pressure of the asthenosphere are so high that rocks soften and partly melt, becoming semi-molten. The lower mantle extends from about 660 kilometers, 410 miles, to about 20,100 kilometers, 1,678 miles, beneath Earth's surface. The lower mantle is hotter and denser than the upper mantle and transition zone. The lower mantle is much less ductile than the upper mantle and transition zone. Although heat usually corresponds to softening rocks, intense pressure keeps the lower mantle solid. Finally, the core is primarily composed of iron, with lesser amounts of nickel. Lighter elements such as sulfur, oxygen, or silicon may also be present. The core is extremely hot, 3,500 degrees to more than 6,000 degrees. But although the boundary between the inner and outer core is approximately as hot as the surface of the sun, only the outer core is liquid. The inner core is solid because the pressure at that depth is so high that it keeps the core from melting. On the other hand, the most well-known feature associated with Earth's lithosphere is tectonic activity. Tectonic activity describes the interaction of the huge slabs of lithosphere called tectonic plates. The lithosphere is divided into tectonic plates, including the North American, Caribbean, South American, Scotia, Antarctic, Eurasian, Arabian, African, Indian, Philippine, Australian, Pacific, Juan de Fuca, Cocos, and Nazca. Most tectonic activity takes place at the boundaries of these plates, where they may collide, tear apart, or slide against each other. Thermal energy, heat, from the mantle part of the lithosphere enables the movement of tectonic plates. Thermal energy makes the rocks of the lithosphere more elastic. Tectonic activity is responsible for some of Earth's most dramatic geologic events. Earthquakes, volcanoes, orogeny, mountain building, and deep ocean trenches can all be formed by tectonic activity in the lithosphere. Tectonic activity can also shape the lithosphere itself. Both oceanic and continental lithospheres are thinnest at rift valleys and ocean ridges, where tectonic plates are shifting apart from one another. Plate tectonics is a scientific theory that explains how major landforms are created as a result of Earth's subterranean movements. The theory, which solidified in the 1960s, transformed the earth sciences by explaining many phenomena, including mountain building events, volcanoes, and earthquakes. In plate tectonics, Earth's outermost layer, or lithosphere, made up of the crust and upper mantle, is broken into large rocky plates. These plates lie on top of a partially molten layer of rock called the asthenosphere. Due to the convection of the asthenosphere and lithosphere, the plates move relative to each other at different rates, from 2 to 15 centimeters, 1 to 6 inches, per year. This interaction of tectonic plates is responsible for many different geological formations, such as the Himalaya mountain range in Asia, the East African Rift, and the San Andreas Fault in California, United States. The idea that continents moved over time had been proposed before the 20th century. However, a German scientist named Alfred Wegener changed the scientific debate. Wegener published 2 articles about a concept called continental drift in 1912. He suggested that 200 million years ago, a supercontinent he called Pangaea began to break into pieces, its parts moving away from one another. The continents we see today are fragments of that supercontinent. To support his theory, Wegener pointed to matching rock formations and similar fossils in Brazil and West Africa. In addition, South America and Africa looked like they could fit together like puzzle pieces. Despite being dismissed at first, the theory gained steam in the 1950s and 1960s as new data began to support the idea of continental drift. Maps of the ocean floor showed a massive undersea mountain range that almost circled the entire Earth. An American geologist named Harry Hess proposed that these ridges were the result of molten rock rising from the asthenosphere. As it came to the surface, the rock cooled, making new crust and spreading the seafloor away from the ridge in a conveyor belt motion. Millions of years later, the crust would disappear into ocean trenches at places called subduction zones and cycle back into Earth. Magnetic data from the ocean floor and the relatively young age of oceanic crust supported Hess's hypothesis of seafloor spreading. There was one nagging question with the plate tectonics theory. Most volcanoes are found above subduction zones, but some form far away from these plate boundaries. How could this be explained? This question was finally answered in 1963 by a Canadian geologist, John Tuzo Wilson. He proposed that volcanic island chains, like the Hawaiian Islands, are created by fixed hot spots in the mantle. At those places, magma forces its way upward through the moving plate of the seafloor. As the plate moves over the hot spot, one volcanic island after another is formed. Wilson's explanation gave further support to plate tectonics. Today, the theory is almost universally accepted.